This is Statistics 243 at Berkeley for Friday, October 10th. Okay, let's go ahead and get started. So we have about a day left of talking about computer arithmetic and precision of numbers, storing numbers, and computing and calculating with numbers. So we've talked some about overflow and underflow and how accurately we can represent a number, and I want to talk some right now. I want to sort of extend that discussion of how accurately we can represent a number and talk about basically what's the spacing between numbers that we can represent. So one way of thinking about this is when we're thinking about real numbers on a computer, they're actually not continuous. They're discrete because we only have a discrete number of bits to store them in. So necessarily, there's only a finite number of numbers that we can actually represent. So leaving aside the exponent part, we've got 52 bits that we can fill up. And so I have all different combinations of zeros and ones in terms of filling up those 52 bits. And for numbers that are a magnitude of around 1, so we're just ignoring the exponent part, that's basically all of the numbers that I can represent. I can't represent anything else because I don't have any more degrees of freedom with which to represent another different, distinct number. So this idea that numbers on a computer are discrete is important in terms of then relating that back to what we've already been seeing about the fact that we can only represent numbers up to 16 digits of accuracy in base 10. Okay, so I thought what we could do is work through a couple examples of this, and what we'll see is that machine epsilon comes back in a different form when we start talking about the spacing of numbers. So for simplicity, let's start by looking at numbers that are an order of magnitude of around 1. So if I want to represent 1 in our representation, which is the -1 to the s times 1 point, and then I've got d1 up through d52 times 2, and I think I had e to the -1023. So I can write 1 as, here's the leading bit, 1, and then just 52 zeros times 2 to the 0. Right? So that would be setting e to 1023. And this would be my representation of what 1 is. Yeah?
Just to satisfy my curiosity, the implementation of storing numbers this way, is that done on a hardware level or an assembly code level? Like when the assembly asks the transistors to add 2 numbers, is the assembly dealing with the E minus or the transistors dealing with the E minus?
I don't know. Yeah, I haven't looked into it at that level of detail. But so now if we think about what's the next largest number that we can represent in this representation, well, the smallest change I can make to this number is just to add a 1 in the 52nd position here, right? And so now what do I have? I have 1.00001. And so if I'm thinking about the discrete numbers that can be represented, well, I have whatever this one is, I have whatever this one is, I have whatever the one is where the next one, which is going to be a 1 and then a 0 here. And that I can just start to enumerate all of the different numbers that I can represent. So now it starts to make sense that if I then think about what is this value, there are going to be values in between this one and this one that I can't represent precisely on the computer. All I can do is basically, if I had a number that was in between these two, all I can do is just either default to truncating or rounding up, or I could choose the one that's closest to it, but I can't get any more accurate than just choosing one of those two, because there's no more degrees of freedom with which to represent the number that's in between these two. Okay, so the difference between these two numbers, the epsilon here, is 1 times 2 to the -52 because of where I've made the change in the 52nd position here. And if we think about what that is in terms of base 16, base 10, I just gave away the answer. I was going to say, can anybody have a guess as to what this is? What this is 10 raised to what power? it's 10 raised to the, it's basically 2.2 times 10 to the minus 16, okay, which we've already seen in the context of machine epsilon defined as we defined it the other day. So basically, the spacing between numbers that we can represent when those numbers are of this order of magnitude of 1 is we can represent numbers basically that are spaced in units of about 2 times 10 to the minus 16. And so if the computer is, in general, choosing sort of the nearest value, either a little bit higher, a little bit larger, or a little bit smaller, so the error in general is going to be about half of this in terms of representing the number relative to what the true value is. So the error is going to be about 1 times 10 to the minus 16. So we've already seen that a lot, right? We've already seen that when we enter a number like 0.1 on the machine, it is 0.1 up to, it's accurately represented for 16 digits, in this case also 16 decimal places, and then there's an inaccuracy, and that's precisely because of this issue here, that I can't represent 0.1 exactly in this representation. Okay, so questions or comments? So that is this. So another definition of machine epsilon is the relative spacing of numbers on the computer. And when the numbers are around 1, it's actually the absolute spacing between the numbers. So that's what we're seeing over there. Yeah.
You can represent 0.1. Base 2. Yeah,
Not
base 2, but that's just 2 to the, it's 1 over 2 to the 0.
1 over
It's not
2.
a slide. Never mind.
No worries. Okay, so machine epsilon is this 2 times 10 to the minus 16 number. It gives us the absolute spacing of numbers near 1, which we already saw, but it's also going to give us the relative spacing of numbers that are either larger in magnitude than 1 or smaller in magnitude than 1. So one way we could think about that is if we have a number that's a magnitude around x, the relative spacing of the next number that I can represent exactly on the computer is basically 1 plus machine epsilon times x. So this is the difference between the next number I can represent and the current number, and then the relative spacing as I get these, then I divide by x. And so obviously arithmetically this equals epsilon. So if I think about sort of applying this formula and what it means, then suppose I have a number like 1 times 10 to the 6th, then the absolute error in representing numbers of that size is going to be epsilon times the magnitude of the number, so that's the absolute error. And so the result is if I think of taking this and multiplying by epsilon, which is about 1 times 10 to the minus 16, or 2 times 10 to the minus 16, I get that the absolute error is going to be about 2 times 10 to the minus 10, which is sort of just another way of saying that when we were looking at printing out a lot of numbers like we did last time, if we see a number that looks like this, we're only going to have 10 digits to the right side of the decimal place that can be represented accurately, because we've used 6 on the left, we've got 10 to the right of the decimal place, and that's the accuracy that we have. And so here's an example. If I try and write out 1,000,000.1, indeed I've got basically 6 places here, and then I've got 10 here, and then I've lost accuracy at that point. Okay, so the next thing I thought we'd do is see this in the context of much larger numbers, and so it might be interesting to do that by looking at what integers we can represent exactly. And what I want to show, what I want us to see here is, for up to fairly large integers, we can represent them all exactly in this representation. So what I'd like you to do is, what we'll see by doing this is that we can go up to 2 to the 53rd and represent integers as large as 2 to the 53rd accurately. But then if we try and increment above that, we're not going to have enough. We're not going to be able to be accurately incrementing in that way. So what I'd like you to do is take a minute and see if you. What I'd like you to do is write out the number 2 to the 53rd in base 2 in our representation like that over there. Write out what 2 to the 53rd minus 1 would look like. And then try and write out what 2 to the 53rd plus 1 and 2 to the 53rd plus 2 would look like. And what we'll see is basically this is the point at which which things break down. We can no longer represent every single integer exactly. So take a minute to try and do that. Feel free to confer with your neighbor, and then we'll reconvene and see what we get.
That's where you start losing precision and places like the one. Yes, they did some precision. So we see. Yeah, that's kind of the point. Like spacing, because it falls within machine epsilon on this scale is a good way to think of it. Because machine epsilon size your order. So on the computer, all of the numbers are relatively small. Well, like why? Because people are so stable.
Okay, so let's see what we've got. So if I want to try and represent 2 to the 53rd, how can I write that in that form? So what do I have to start with? So I have to start with a 1 because that's the hidden bit that's always there. So 1 point something times.
This is base 2 raised 10.
So yeah, I want to write these guys in terms of base 2.
Gotcha.
Gianni? Okay, so a bunch of zeros, and then okay, and then 2 to the 53rd. So there's nothing too much going on here. Okay. So this is one. This part represents 2 to the 53rd. This is 0 times 2 to the 52nd. This is 0 times 2 to the 51st. So 52, 51, there are 50. Wait, I can get this right there. 52 of these. This was 52. So this must be 1. So this is representing times 2 to the 1, right? And this is representing times 2 to the 53rd. And this is representing times 2 to the 52nd there. So I can think of this as 1 times 2 to the 53rd plus 0 times 2 to the 52nd plus 0 times 2 to the 51st plus 0 times 2 to the 1st, and that's going to equal, well, I've already sort of moved this over. So that's going to equal 2 to the 53rd. Okay. Okay. So what about if I want to go 1 backwards here? What's that going to look like? Kelly?
It's going to be the same as the above, except for instead of all of yours, you have all the ones.
Yep. I'm going to have all 1s. And what am I going to have here? Times 2 to the 52nd. Yep. So what does that mean? That means this is now representing 1 times 2 to the 52nd plus 1 times 2 to the 51st plus 1 times 2 to the 50th, plus 1 times 2 to the 0. So that equals a 1 there. And so that's going to be 1 times 2 to the 52nd plus 1 times 2 to the 0, and that should indeed equal 2 to the 53rd minus 1. Okay. One of the reasons I wanted to write this out this way is now if we think about this, if I decrease this one by another 1, if I decrease this from a 1 to a 0, I'm decrementing by 1 times 2 to the 0, I'm decrementing by 1. So at this point, I'm working in units of 1s where I'm decrementing. So I can subtract another 1, and I'll get 2 to the 53rd minus 2. So you can see I've got all of the, you can sort of start to see that it would make sense. I've got all the integers up to 2 to the 53rd. I can represent 2 to the 53rd, I can represent 2 to the 53rd minus 1, I can represent 2 to the 53rd minus 2. By analogy, you could work backwards and see I can basically work my way all the way backwards to 0. So I can represent all of those integers precisely. But now we should be starting to see what's going to go wrong at this point. Right? So what is this number going to be? It's going to be what's the next largest number that I can make this? What can I change here? The last digit. So I can make this a 1. We're in base 2. So this could be 1.01 times 2 to the 53rd. But this is representing 1 times 2 to the 1st. So what is this number? This is 2 to the 53rd. That's 1 times 2 to the 53rd plus 1 times 2. So this is equal to 2 to the 53rd plus 2. Sorry. Okay, so now I've just written, right, so that I was supposed to be trying to see if I could get a plus 1 here, and I can't. Right? So now at this stage, every time I'm going to be incrementing here, I'm working where I'm incrementing by 2 instead of incrementing by 1. And it's going to get worse and worse once this becomes a 2 to the 54, because then I'm going to be incrementing by 4 instead of by 2, and so on and so forth, all the way on out to as much as I care to think about that. So questions about that? So the biggest integer that I can represent in this way, where I can actually increment by 1 and get all the integers, is 2 to the 53rd, and then I start having things not work. Or, I mean, they work, but yeah, they don't work. You know what I mean. So let's actually look at that. We can see that I can represent 2 to the 52nd and 2 to the 52nd plus 1. That's fine. You can see those get incremented by 1. Presumably R is doing the calculation correctly, and that is actually that value. If I do 2 to the 53rd, we can see what it is. It's this 900 whatever gazillion number. But now let's try and increment it by 1 and see what happens. It just stayed the same. So it chose, in this case, I guess it didn't really matter. It could have either gone up or down. It chose to use the nearest lower number instead of the nearest higher number. But this issue is exactly basically what I wrote out here. I can't represent this number in here exactly in my representation, so it has to choose to either use this one or use this one. In this case, it's equidistant, and so for some reason or another, it chose to use the lower one. But if I did 2 to the 53rd plus 2, that's fine. I can do I can get 994. Same logic as over there. Okay. So so once you sort of think about this, then this makes sense. But if you start looking at this and start putting in these numbers, you're like, why did it just jump by 2 and then not jump by anything and then jump by 2? That's the purpose of working through this. And if we tried to do this with 2 to the 54, what we'll see is the business I was just saying about the jumps being in units of 4 now. So here's 2 to the 54. I try and add 2 and I can't do it. Instead, I get the same number, but I try and add 4, and I can indeed add 4 to that. But this is the 2 to the 53rd, which was as big as we could get before we started losing accuracy, is a pretty big number. So we can represent most integers that we generally will work with exactly. We just when we get too big, we can't. Okay. Any questions or comments? So the same thing basically happens on a smaller scale. It's a little bit harder to think in terms of base 2 when working with small numbers. This was a little bit, at least in my mind, easier to write out. But if I try and take a number like this one, which has 16 digits, and then in the 17th place, I try and increment it by 1 here in base 10, we'll basically see similar sorts of things going on, which is here's the best we can do in terms of representing this number in our base 2 representation. If I increment it by a little bit, I can see that that it does change. I am able to, I do get a different representation. It's still not only accurate to 16 digits, but this is the best I can do for this number, this is the best I can do for this number. In some cases, when I increment by another one, it turns out this number, which is precisely the same for these two, is the best I can do in terms of the nearest accurate, the most accurate nearest value for both of these. It just happens to be that way. If you could play the game of writing out all these numbers in base 2, and you would see that it is indeed choosing the best that it can to do to represent these numbers. So very, very similar things are going on both for very large numbers, numbers around 1, and very small numbers. It's about the fact that the floating point is basically floating back and forth, and I always have basically 16 digits of accuracy. It's just the magnitude of those digits changes. In R, we can actually work with numbers in higher precision if we want to. There's this package called RMPFR that would allow you to, for example, represent pi to, say, 260 digits of accuracy if you wanted to. I won't bother to go through that, but if you were interested in playing around with that, you could. And I think this will allow you to do more accurate arithmetic if you really needed to be more accurate about your arithmetic calculations. Let's see. Okay, so let's now turn and talk about some more of the explicit implications of all this for what kinds of calculations we can do accurately and when things can really go quite wrong. And we've already seen a little bit of this the other day when I was talking about catastrophic cancellation. But before we get back to that, let me just show you that just like on a computer, numbers are not what they seem in the sense that they're discrete. Real numbers are discrete instead of being continuous and uncountable. The order of what's this rule where if you multiply numbers in different orders, you get the same answer? Is that associative or commutative? That's associative. Okay. So I should be able to multiply 3 numbers in any arbitrary order, and I should get the same answer, right? Well, as we've been seeing on a computer, all is not as it appears. And if I ask whether the result of multiplying the first one times the second one times the third one is the same as the result when I multiply them in the reverse order, it says, no, indeed, those two are not exactly the same. Okay? And if I just look at what res 1 is, and I look at res 2 is, they're almost exactly the same, right? Like up to the 16 digits here, it looks like things are fine, but they're very slightly off. And that comes from the fact that multiplying them in different order involves apparently some different operations in terms of doing the arithmetic, and it matters what order you do it in, and so you get something a little bit different. And that if you really wanted to delve into this, that might start to get towards some of Daniel's questions about like what is the computer really doing when it's doing a calculation, and where in in sort of all the intricate hardware and software details is it doing all that? Yeah, Mike.
So it seems like you would want those to be the same. Why would R not just fix that for you, or why wouldn't that be part of it?
Well, how would it fix it, I guess, is the question. Right? I mean, what we're seeing is there are fundamental limits to what we can do in terms of storing numbers accurately. And unless there was an R function that somehow decided arbitrarily that it wanted to do it, that it should always multiply them in this way. But there's no way there's nothing R can do to sort of magically make that happen.
Just round up to 16.
Yeah, I mean, I guess that's one thing. It could, instead of giving you back basically the nearest approximation that it can represent, I guess it could do some rounding, but it chooses to basically leave things as best it can do. Did you have a comment or a question?
I was just gonna say I had some function before where I was getting this issue and I was like, what is happening? And the way I fixed it, I don't know if there's like a better way, but I just rounded it up to like a certain digit and then it fixed the problem. So I rounded both numbers and you can say like digits equals.
Yeah, so you're saying if you wanted to do a comparison?
Yeah, like
yeah,
I
so
need to get
so
that to say true.
yeah, so there are basically two things you could do. One is you could round the numbers such that you weren't trying to get more than 16 digits, and then you could compare them. In the notes, we might not go into this in a lot of detail. If you look at, for example, the all.equal function, I think it's all.equal, you'll see in the title of this, it says test if two objects are nearly equal. And you'll see in here there's an argument called tolerance, which is pulling machine epsilon off as the default value. So basically, another way to say a different formulation of what Greta was saying is, instead of rounding, just check to make sure that the two numbers differ by no more than machine epsilon. Sometimes we'll put a little fudge factor in there. We might make it twice machine epsilon. But that's the basic idea. Is only if you've got real numbers, only compare them to within the accuracy that we know that we can deal with these numbers in. Comment, Chris? Yeah. Question?
In theory, you could also use a symbolic algebra system which would just maintain like what were the original like divisions used to create the decimal, and that would allow you to have arbitrary precision.
Yeah, I mean, so there are ways you could do it symbolically. There are ways that you could, and this is where that RMFP, MPFR, or whatever it is, gets, where you could say to the computer or to R, use more than 8 bytes to represent these numbers, and then you're going to be able to get more accuracy. It's not that there aren't ways around this. It's just that for most uses, we don't need more accuracy than this, and if we try and get more accuracy, it's going to involve either more computation or more storage in terms of storing the numbers. Let's see. Okay, so that was one implication of thinking about computations. We've already seen a little bit of this about comparisons, that we can do this safely. Here we're explicitly representing them as integers. We can also do this safely because we've already seen that integers up to 2 to the 53rd can be represented exactly. So those should both evaluate to true, but we also know that this comparison, this third comparison, the 4.1 minus 3.1 cannot be done exactly. And another thing, and actually this does follow along with what Greta was asking about. If I was thinking about comparing these numbers and saying, are those numbers equal? Well, if I look at them written out like that, obviously they're not equal. But if I look at the fact that they only differ in the 17th position there, to the computer, they are essentially the same number because it can't work with accuracy. It doesn't have accuracy any more than the 16 digits. So here I'm writing my own approximately equal function that basically says if the difference between the two of the numbers that I pass into this function is less than machine epsilon times the absolute value, this absolute value basically tries to reflect the fact that I need to know what the magnitude of the number is and multiply that by machine epsilon, which has to do with the x times epsilon over there. Then this would be writing my own function to do that comparison to see if the two numbers are the same up to the accuracy that we can represent those numbers on the computer. This all.equal in R is R's built-in way of doing the same thing, but here I just coded it up myself, basically. Okay. All right, so let's turn to some more about calculations and when things can go awry in terms of doing calculations. So here's the example of catastrophic cancellation that I already showed actually a little bit before, which is suppose I subtract these two numbers. Both of these numbers can be represented up through 4 places here past the decimal point. So in some sense, I'm like, oh, I can represent those numbers pretty accurately. But if I subtract them, and I look at the difference between the two of them, well, the difference between those two numbers is just 0.560000. So if I were just putting 0.56000 into the computer as a number, if I just said x gets 0.56, I wouldn't need to write all these zeros, then what I would see is, like we've seen with 0.1, this should give a number that up to 16 places it has accuracy up to 16 places. But if I get the number by virtue of having done a calculation like this, what's going to happen? Well, when I subtract these two numbers, all of these digits up to the 4 are going to cancel out with all of these digits. And so what I'm trying to do is basically subtract this part and this part, but only 4 digits are accurate here, and only 4 digits are accurate here, and all the rest of it is, it's not garbage, it's not arbitrary, but it's like we were talking about before, it's basically the nearest approximation. And so what do I get? Well, not surprisingly, I get back a number that is accurate up to 4 places, but the remaining places are not accurate. Okay. So it's very different if I assign the number in to start with versus if I get the number by a calculation, and then this number is not represented particularly accurately, only with 4 digits of accuracy. And that basically happens regardless of whether I'm working with large magnitude numbers or small magnitude numbers. If I'm doing a subtraction such that some, one or more of these digits is just basically going to cancel with those, all of the accuracy that I had that I was using for those digits is basically thrown away in doing the subtraction. Okay, same sort of thing will happen with numbers that are much smaller in magnitude. So if I do this, I can think about what I would expect. Here I can these are going to be accurate. Another 4 of these are going to be accurate here. But I'm going to cancel out 8 of my digits of accuracy, so I'm only going to be left with 4 digits of accuracy in the resulting difference that when I calculate the difference. And I can see that here. Okay, so here we go. I've got here are my 8 digits, and then things decay after that. Okay. So that's called catastrophic cancellation. This sort of thing could pop up in other sorts of calculations. So one example of this would be, suppose you were computing a sum of squares, and okay, so I know that I can compute a sum of squares like this as either the sum of the quantity minus the mean and the whole quantity squared and then summed up, or I can compute it as the sum of each individual x squared and then subtract off n copies of x bar squared. Okay, either way, that will give me an s squared, a sum of squares calculation. But if I were to do it in this way and not be thinking about the fact that I'm working on a computer and I have limited precision in my calculations, well, this is usually going to be fine if the x's aren't too big. But suppose that what I was doing was I have 3 x's, all of them are order of magnitude of 10 to the 8th, and one of them is 10 to the 8th minus 1, the other one is 10 to the 8th, and the third one is 10 to the 8th plus 1. Okay, so I'm trying to calculate a variance or a standard deviation of numbers that are very big, where the variance is not very large relative to the magnitude of the numbers. Okay, so I can go ahead and do that, and if I do the calculation, go back to R here. I get that the sum of squares is 0. Even though obviously, basically what I have is I'm calculating the sample standard deviation of basically the numbers minus 1, 0, and 1. Okay, so I've obviously made a very large error in terms of what my sum of squares is, and you can sort of see where it's coming from. Well, I'm subtracting 2 numbers where I'm trying to find a very small difference between 2 numbers that are very large in magnitude. So there's been a bunch of catastrophic cancellation going on in terms of this subtraction. So much catastrophic cancellation that I'm basically getting back an answer that is garbage. Whereas if I actually did it by first taking all the numbers, subtracting off the mean, which is just going to be 10 to the 8th, then I get, well, once I subtract off the mean, then I just have minus 1, 0, and 1, and then I can do the sum of squares easily and precisely. And so then I get that the sum of squares is actually 2 in this case. Okay, any questions about that? Okay, and we've sort of already seen some of this as well. So I just said that catastrophic cancellation can be a problem when we're subtracting 2 numbers that are very similar in two numbers that are almost the same, and I'm trying to find a small difference relative to the magnitude of the 2 numbers that I'm subtracting. I can also run into problems if I'm trying to subtract 2 numbers that are very different in magnitude. So here, if I subtract these 2 numbers, well, the problem is that if this number gets small enough relative to this number, I'm trying to subtract a very small amount off of this number, but this number is only represented accurately up to a certain number of digits. So if I were to try and subtract off something that was smaller than the amount to which the number of digits that I can represent this accurately, I'm not going to be able to actually have any accuracy. That's sort of like when we were saying add epsilon to 1. How small an epsilon can we use before once we add 1 and epsilon, I just get back 1, and basically I haven't been able to preserve the epsilon. And so similar sorts of things happen if we're adding and if we're subtracting a large number and a small number as if we're adding a large number and a small number. And so you can see here that basically the result is this has not been, this is smaller. So I have 4 digits of accuracy after the decimal place in this number, so 0.000. But this 1 is even beyond that 4th 0 here, and so I can't actually get an answer that reflects the fact that I've subtracted off that small magnitude number, and so I just get back what I originally got. So this is basically the same as when we were trying to add epsilon to 1, and we saw that once epsilon was as small as machine epsilon, I could no longer get anything different than 1 when I added epsilon to 1. Let's see. Okay, so that is sort of things that can go wrong when we are, because of the limited accuracy of with which we can represent these numbers, both big numbers and small numbers. The other thing to point out here is going back to underflow and overflow. We're limited in how large a number and how small a number we can represent, or that we can represent. So we can't work with numbers that are any bigger than 1 times 10 to the 308, or numbers that are any smaller than 1 times 10 to the minus 308. So if we were to start to do some calculation where that calculation would push us over 10 to the 308th, or push us under 1 times 10 to the minus 308, we're going to end up with, in this case, R would spit back, oh, you've got infinity, or you've got 0, and we'd basically no longer be able to work with those numbers. So those seem like big numbers, but it doesn't take very many multiplications to get to numbers that are as big as 10 to the 308th or as small as 10 to the minus 308. So it's very often the case that you might be doing something like, you might be taking a product of numbers and dividing by another product of numbers. And if taking this product got me up above 10 to the 308th, then I'm going to have trouble with doing this division here. It pops up a lot, as I was mentioning, with calculating likelihoods, that if you have each term in your likelihood is, say, 0.01, and I multiply enough of them together, I'm going to get a number that's smaller than 1 times 10 to the 308th, and I'm just going to get back a 0. So the usual story in terms of dealing with this is, as long as we're aware of this, it's not a hard problem to solve. We just work on the log scale. If we're taking products of numbers, either big ones or small ones, just work on the log scale, and that's going to be, the exponent. This is equal to the exponential of the log of this, and of course the log of the difference of a product is going to be the difference of the sum of the logarithms of the individual elements. Okay. And so that's sort of, for the most part, that's the solution that we work with whenever we're working with a product, is to work on the log scale. Okay, any questions about that? All right, so I just wanted to show, to wrap up here, I wanted to show a little example of where this comes in a somewhat more complicated way. So this example includes both this idea that we generally want to work on the log scale and an example of using another trick to try and get around some of these sorts of complications that can arise. So let me try and motivate the problem here. So what this is, and this came up in my PhD thesis because I was trying to do a calculation like this, and I was talking to my advisor, and I said, I'm running into this problem that I can't do this calculation. He said, oh, yeah, that's a known problem. The student that I had 2 years ago, he realized that I could do this trick to get around this problem. And so then I went ahead and used that trick. So the idea is to see what the trick is. Okay, so what the calculation I'm trying to do is something that looks like this. So this comes up if you're trying to figure out something called the predictive density. So this is the density of some new data, some held out data or some test data, given some training data y and some covariance. So suppose you fit some sort of regression model where you regress y on x, and now you want to say, well, basically what's the likelihood or the probability or the density of new observations? Okay, so you might want to make a calculation like this. And so one place this might come up is if suppose you had two different competing regression models, and you want to see which model is better. It's usually a good idea to fit two models and then test the two models on held-out data, on cross-validated data or testing data, and then see which of the two models does a better job in predicting these new observations. Okay, and so this avoids the problem that you might be overfit. One of the models might be overfitting, and it might look like the model does better on the training data, but in reality it's overfitting and it's not going to generalize to new data very well. So you might want to calculate this quantity for each of two different regression models. And in a Bayesian context, which some of you may have been exposed to and some of you may not have, this quantity is basically an integral of the predictive density given the value of some parameters. So these might be these, for example, would be the regression parameters in the model, averaged over the posterior density of those regression parameters. So this calculation basically takes account of the uncertainty in the fact that you never know exactly what the regression parameters are, and you want to account for that uncertainty in the calculation. So this is the integral we're trying to calculate. It turns out that you can approximate this integral by basically taking draws of different possible regression parameters from this posterior distribution. And if I do that, I convert this into a sum where this integral becomes this sum over different possible values of these regression parameters. Okay, so the motivation is maybe interesting, or maybe it is not. Maybe if you haven't seen Bayesian statistics, this might have gone a bit over your head, and that's fine. But suppose I've gotten to this stage and I know this is the calculation I want to do. I want to sum up over a bunch of different theta j values this predictive density here, where these are the test data, these are the covariates. I suppose I should have an X star because it would be the covariates relevant for these observations. And these are my coefficients for my regression model. So just think of this as predicting Y star from X times X star times beta, but in this case beta I'm calling theta. So I've got Y star, or Y star hat, my best prediction is X star times my theta j, and this is like the beta in a regression. Okay, so now for the first thing there are going to be sort of two sets of things we have to do to try to deal with this calculation. So you can sort of imagine what's going to happen here. Right away we have the problem that I just mentioned, which is we're trying to multiply together potentially a lot of numbers here. They might be somewhat small numbers, and if I multiply enough of them together, this might underflow and give me a number back that's less than 10 times to the 10 to the 308, 10 to the minus 308. So the first thing I can do is I see this, I say I have a product. I'm a statistician, so immediately I say, okay, I need to work on the log scale. So now I take the log of this inner part, and this is just the exponential of the log of this, and the log of this is just the sum of the logs of the individual terms. Okay, so that's fine. So I can do this summation of these log predicted density values, and I sum them up. And maybe on the log scale, I get that my log density is minus 1024. Like if you worked with log likelihoods, this is not a number that would probably surprise you. You might very well have a log likelihood that looks like that. And so, okay, I get minus, for a given value of j, let's suppose I get minus 1024. So that's for j equals 1. And now for the next value of j, because remember I'm doing this in this summation over the different possible regression parameters that I've drawn from this posterior distribution, maybe I get minus 1022. And then maybe for j equals 3, I get minus 1027, something like that. Well, now what do I need to do? I need to exponentiate each of those values and then add them together. Okay, so let's see if I could do this, and we'll see if I've chosen these numbers to sort of work for the example that I'm trying to draw out here. Okay, so I do exp of minus 227. Oh, right, that's a 0. Right, so every one of these that I try and exponentiate, once I exponentiate it, I get a 0, and my calculation falls apart. So the question is whether there's anything. Let's go back to the PDF here. So what I've done here, I guess I'll just relate what I just said there to what the change in notation here. So what I've done is I've just said, well, you know what? This summation, which is the minus 1024, the minus 1022, the minus 1023, those are the different. That each one of those is a different value for a different j of this summation. Let's just call this whole thing v sub j. So here's v sub 1, here's v sub 2, here's v sub 3, et cetera, et cetera. So the question is, how can I possibly do this sum when I can't exponentiate into the individual values because I get back a 0 because of underflow? So let's pause for a minute, see if folks have any ideas about that. Consult with your neighbors, and we'll see if we can see if either you can come up with the trick that my elder grad student came up with, or if there might be some other idea that would solve this problem. So I think I'll actually leave this hanging. I won't call on anybody on Monday, but I'll leave it hanging. I won't call on anybody on Monday, but if you are curious, you're interested in it, mull it over the weekend, and we'll talk about it at the beginning of class on Monday. One way that might be helpful is just sort of write it out like this: exp of the v1 plus exp of the v2 plus so on and so forth, and see if that way of representing it sort of stirs any ideas. Okay, so we'll just take 3 or 4 minutes at the start of class on Monday to do that. I haven't yet put up the next unit because I'm a little bit behind, but we're going to launch into parallelization on Monday. On Wednesday, we're going to start talking about large data sets, databases, Hadoop, and distributed file systems and things like that. And the other thing I want to mention is in section on Monday, Jared's going to give you an introduction to Python. And that's going to be useful because I'm going to ask you to do a very little thing in the next problem set on using Python and comparing it to R. And because when we work with MapReduce and some Hadoop stuff, either the end of next week or the week after that, we're going to have to use Python to interface with it. So that's in part why we're doing it.
I have 2 questions.